So we've seen how the semiconductor action works in a diode. Now let's move on to something a little more sophisticated and something that has a little more utility and functionality. We're going to look at the DC operation of the bipolar junction transistor, or for short, the BJT. A transistor is a semiconductor device that controls current between two terminals based on the current or voltage on the third terminal and is used for the amplification or switching of electrical signals. The basic structure of the BJT determines its operating characteristics. DC bias is important to the operation of the transistor in terms of setting up proper currents and voltages in a transistor circuit. So we're going to see how, just like the diode, setting up that bias will allow current to flow through the other two ports, and when we start talking about the amplifier, how it controls the gain on the output. The bipolar junction transistor then is constructed of three doped semiconductor regions separated by two p-n junctions, as shown in the epitaxial planar structure in the figure A. So there's your epitaxial. The three regions are called the emitter, the base, and the collector. Representations of the two types of bipolar transistors are shown in B and C. So in B we have the NPN transistor. In C we have the PNP transistor. One type consists of two N regions separated by a P, and the other consists of two P regions separated by an N region. The PN junction joining the base region and the emitter region is called the base emitter junction. The junction joining the base region and the collector region is called the base collector region. A wire lead connects to each of the three regions as shown. These leads are labeled E, B, and C for emitter, base, and collector, respectively. The base material is lightly doped and very narrow compared to the heavily doped emitter and collector materials. So in the figure we can see the schematic symbols for the PNP and the NPN bipolar transistors. NPN, we typically say that's not pointing in. You can see the arrows pointing out to the emitter. In the PNP we call it pointing in. The emitter arrow is pointing toward the base. The term bipolar refers to the use of both holes and electrons as charge carriers in the transistor structure. Although both PNP and NPN transistors are commonly used, in our discussions we will predominantly use the NPN transistor to illustrate our concepts. So get used to using seeing and understanding and using these schematic symbols. For transistor biasing, in order for a transistor to operate properly, as an amplifier, the two p-n junctions must be correctly biased with external DC voltages. The figure below shows the proper bias arrangement for both a PNP and an NPN transistor. Notice that in both cases, the base emitter junction is forward biased and the base collector junction is reverse biased. This is called forward reverse bias. So if you look at the diagram here, you can see the setup here. You notice the biasing: base collector, reverse bias, negative positive. On the base emitter, forward bias, positive, negative. Okay, just the reverse on the PNP. on the PNP. Transistor currents then, the directions of current in an NPN and a PNP transistor are shown. An examination of these diagrams shows that the emitter current is the sum of the collector and the base currents and is expressed mathematically as emitter current equal to collector plus base current. Okay, and we can see in the diagram here how that is shown diagrammatically as well as the schematic symbol. As mentioned before, the base current is very small compared to the emitter or collector. The capital letter subscripts indicate DC values. These direct currents, emitter, base, and collector, are also related by two parameters. The DC alpha, or alpha DC, which is the ratio of the collector current to the emitter current, and beta DC, or DC beta, which is the ratio of collector current to base current. Beta DC is the direct current gain and is usually designated as HFE on transistor data sheets. The collector current is equal to alpha DC times the emitter current. Okay, so all of these terms are terms that you'll have to get used to. Again, start writing them down in your notebook and keep track. Make notes to yourself of what they are in fact telling you. Alpha DC typically has a value between 0.95 and 0.995. Generally, alpha DC can be considered to be approximately 1, and therefore the collector current is equal to approximately the emitter current. The collector current is equal to the base current multiplied by beta DC. Again, we can see that in the diagram, in the mathematical notation. Both beta DC typically has a value between 20 and 300. Write that down. Depending on the type of transistor, some specialized transistors have much higher values. Okay, there's a lot that was just heaped on you here. Go back, read your book, review the video here. Make sure you understand those fundamental concepts.